Okay, we're going to look at section 6 here, which is reaction mechanisms. Okay, reaction mechanisms are just the process by which a reaction occurs. Okay, it's a list of what bonds are broken and what ones are formed and in what order this happens. Well, the first one we're going to look at here is an elementary reaction, and this is the process that occurs in a single step. All right, the number of reactants that participate in that particular reaction in that one step is what we call molecularity. If you have one molecule, that's called unimolecular. If you have two molecules, that's called bimolecular. And if you have three molecules, which is very rare, that is termomolecular, because that means that I have to have three molecules that need to orient and collide all at once, all at the same time, with all the right energy to get the reaction to occur. So that's why things are usually unimolecular or bimolecular. Okay, now if we have multi-step mechanisms, which means you have to have a sequence of elementary reactions to actually get it to occur, the steps must equal your overall reaction. So it's kind of like that Hess's law thing we looked at a long time ago. All right, and substances that are formed and then consumed again are what we call intermediates. So let's look at an example here. It says, it has been proposed that conversion of ozone into O2 proceeds by a two-step mechanism. Describe the molecularity of each elementary step in the reaction. We're going to write the overall reaction and identify any intermediates. Now, reaction mechanisms are just proposed a lot of times. We have to know these by experimentation, and a lot of times people don't actually even know if that is the actual right number of steps, and there can be also different ways that will make the same overall reaction. So this is one proposed way to get ozone to turn into O2. So in the first one in A, okay, my molecularity. Well, for the first reaction, I have one reactant, so that's going to be a unimolecular. In the second reaction, I have two reactants, so that one's going to be bimolecular. In B, it asks us to write the overall reaction, which we have done before. So what I need to look at here, okay, is what's going to kind of cancel. Well, what should cancel is my O here, okay? And I have how many O3s total? I have two, so I have two O3s. The O's cancel because I have one on the right and one on the left. And then I have three O2s. And we notice that I have 6 O's total on both sides, which is good. C asks for the intermediate, and that is the one we just crossed off. That's one that gets formed, and then we use it up in the next step. So O is our intermediate. The speeds of the elementary steps for a reaction dictate the overall rate for the reaction. So how fast or slow each step is will dictate how fast or slow the overall reaction is. For an elementary reaction, the rate law is based on its molecularity. So if I have a reaction that occurs in one step, if it is unimolecular, okay, the number of moles of my reactant were to increase. So if I would have something like going from A to B, that's unimolecular, I have one reactant. The number of moles of my reactant goes up. Okay, that means the number that reacts increases, which makes it a first order reaction. Okay, so for something that is unimolecular, my rate is going to be equal to my K times whatever A is, or the concentration of A. Now, if something is bimolecular, that's where we're going to have like A plus B equaling C. I have two things that have to react and collide to make my product. Okay, if I have twice the number of A, and that means my number of A and B collisions is going to double, which means that it's overall a second order. Which means that my rate law is going to be, something overall to the second. Now, whether it's A to the first, B to the first, or A to the second, B to the 0th, or B to the second, A to the 0th, that you really don't know. But it's something to the second power there. Okay, the last thing here with this, and kind of write this kind of underneath the bimolecular there, is that it's actually hard to tell if a reaction is elementary or if it's a group of reactions. Coefficients of an elementary step do actually correspond to a rate law, but you can't always tell if the equation is elementary. They're going to have to actually pretty much tell you that that is an elementary step in order to be able to know whether or not I can use those coefficients. Because you really just can't tell by looking at a reaction what other little reactions are going on kind of behind the scenes to make that reaction occur. There might be 2 or 3 different intermediates. You honestly don't really know unless you go through and actually do a few experiments to try and figure out kind of what's going on there. And a lot of times even you can't even tell then. So there we go with that, okay? On the back page of that, then you have a chart which talks about the unimolecular and bimolecular and the termolecular. It has examples there. Notice here how it has 2 examples for bimolecular. It could have A plus A or A plus B. All right. Now, A plus A means that I have like maybe 2 CO2 or 2 O3. I have 2 of the same thing. Okay, so if the following reaction occurs in a single elementary step, predict the rate law. Okay, so I have 2 things going on here. I have a bimolecular reaction. Okay, if one of these was a 2, I would have a termolecular reaction. So then I would have 3 things that would have to collide. Okay, even though they're not 3 different things. But it's not. So I have a rate equals my K times the concentration of H2 times the concentration of Br2. And that there is my rate law. Okay? And now we'll talk about the rate determining step for multi-step mechanism. Okay, often there is one step that is slower in a reaction, and we call that a rate determining step. Okay, this will limit the overall reaction rate because you can't go any faster than the slowest step. And that step will be the one that governs the rate law for the reaction. And for example, okay, you have this picture right here. And these are cars at a toll booth. Okay, we have Plaza A and we have Plaza B for both of them. Okay, and this first one, this Plaza A is my rate determining step because notice how many cars are backed up there. So no matter how fast this person here in Plaza B works, it doesn't matter because Plaza A is the one holding everybody up. Now in the second in B here, now I have Plaza B is the one slowing everybody down. So Plaza B is now my rate determining step. Okay, because now the cars can only go as fast as they can get through B. So it's all about your slowest step, and you can't go any faster than your slowest step. So let's look at mechanisms for reactions with a slow initial step. So I'm going to write the reaction out, okay, that was determined experimentally. I'm going to have my 2 steps, and then we're going to talk a little bit about it. Okay, so here's my overall reaction that was determined, or that I'm looking at. Okay, and the experimentally determined rate is K times the NO2 squared. So that's what I'm trying to figure out how we could possibly get some reactions to go together to get that rate that I know what that's supposed to be based on in my experiment. Well, somebody proposed 2 steps. Okay, they proposed NO2 plus NO2 yields NO3 and NO for step 1, and then step 2 turned the NO3, added CO, and made NO2 and CO2. Okay. Now they also realized here that this was my slow step and this step occurred very quickly. Okay, that means that my rate constant for 2, okay, is much larger than my rate constant for 1. We also look at these. We have NO3 that got formed and then NO3 that got used up. So NO3, that is an intermediate, and step 1 here would be my rate determining step. Since it's bimolecular, I have 2 NO2s here, okay? That's how I get this rate law. Because I would have my rate equal to my constant times NO2 squared because there are 2 NO2s. It's bimolecular. Okay, so let's look at the next reaction here. It says the decomposition of nitrous oxide, N2O, is believed to occur by a 2-step mechanism. We're going to write the overall reaction, and then we're going to write the rate law for the overall reaction. So kind of think Hess's law, like whatever's on the right side adds up to whatever's on the left side. If it's on both sides, it cancels. Okay, so overall, if I write this out, I'm going to have N2O plus N2O plus O yielding N2 plus N2 plus O plus O2. Well, the O's cancel. I've got one on the right, one on the left. I've got 2 N2Os. I have 2 N2s and 1 O2. And I look at both sides, we're bound. So there's my overall reaction. Now I'm going to write the rate law for the overall reaction. Well, that is based on my rate determining step, which would be this one right here, the first one. So my rate is equal to K times N2O because it is unimolecular. There's nothing else going on there. It's to the first order. All right, now mechanisms with a fast initial step are a lot more tricky. Okay, I'm going to write out the reaction here that we're going to look at. Okay, so here's the reaction we're looking at. NO plus Br2 yields NOBr. The experimentally determined rate law was that rate equals K times NO squared times Br2. So they did something very similar to what we did in our reaction in the lab. We had to determine what the overall rate law was. Well, it's very unlikely this is an elementary reaction because I have three things here that have to collide in order to make my product. So it's probably not going to be termolecular, which means I probably need 2 steps to get this one to occur. And an alternate idea here is that I could have step 1 be NO plus Br, NOBr2, and this is going to be a fast step. And we're actually going to draw a double arrow for this one because it's so quick that it goes back and forth. My second step here is going to be NOBr2 plus NO. It's going to yield 2 NOBr. My step is a slower step. Okay, so if we add these up, I get my overall order. Okay, my NOBr2s, which is going to be my intermediate. Okay, the guy's here in green. It gets formed and then I use it. Alright, so what can happen if this is my slow step, the second one. So I'm probably going to have a rate law. It's going to look like this. Rate equals K times NO times NOBr2. But that is not my experimentally determined rate law. That's not what I noticed in that reaction. So we're kind of going to do a little bit of substitution. And what's going to happen is we're going to actually express our intermediate in terms of NO and Br. So we're going to change this guy right here. We can look at NOBr2 in a couple of different ways. Since I talked about that first step being so quick, we're actually going to have some NOBr2 that is going to react with NO. We're going to have some NOBr2 that's actually going to go back this direction and decompose. Well, since number 2 is really slow reaction, not a lot of that NOBr2 is actually going to go into reacting with the NO. So most of it's actually going to decompose and be in step number 1. Well, my forward and reverse reaction rates, if I'm at equilibrium, are going to be the same. So for my step number 1, okay, K times NO Br is going to be equal to K times NO Br, since my forward and reverse reaction rates are the same. I'm at equilibrium. So what we're going to do is we're going to actually kind of solve for this. Okay, I'm going to get rid of this on the right side and divide by it. Okay, now I've got this stuff that I know that I can actually plug in here. Okay, and since we've got K over K, the rate constant is the same, so those cancel. So in essence, I have NO and Br here that are going to get plugged in for this. Well, if I plug those in, I'm going to have rate equaling to K times NO times NO times Br. Oh, and I forgot my 2. So I have really NO squared times Br2. And that's what we get. So I just wrote out right there what I was saying throughout the problem. Okay, now we're going to show that the following mechanisms for equation 14.24, which are the 2 right there, also produces the rate law consistent with the experimentally observed one. So actually what we just looked at, that same rate law, we're going to show that these 2 steps will actually also equal the earlier proposed rate law. Well, I noticed that this is my fast step, this is my slow. This is so quickly, this is actually at equilibrium. Well, if I'm going to go by my slow step, which I usually should, I'm going to have rate equals K times N2O2 times Br2. I know that's not right because I know my rate law should be K times NO squared times Br2. So I need to get this N2O2 out of there, which is okay because this is actually my intermediate. It goes back this direction an awful lot, which means that my rate constant for 1 It's going to be NO squared because there's two of them, the forward reaction. The reverse reaction is going to be my second one, or K to the, they have it here, not negative, not 2, but negative 1, because going back the other way. Going to be based on N2O2. Okay, these two are equal because they're at equilibrium, which means then I can just take and plug that in for there. Because I can move it to the other side. I move my K to the other side, I solve for N2O2, and that's what I get. So I just plug that in, and I have the exact same rate law as I did before, which is that one. Okay, section 7 deals with catalysts. Okay, catalysts are substances that change the speed of a reaction without undergoing a permanent chemical change themselves. There are two types of catalysts. There are homogeneous catalysts and there are heterogeneous catalysts. Okay, homogeneous catalysts are in the same phase as the reacting molecule. They again are present at the beginning and at the end. All they do is lower the activation energy or our frequency factor. And we look here on the right, okay, my uncatalyzed reaction starts off with my reactants, and then there I have the activation energy that I have to achieve here, and then I have my products. Well, a catalyzed reaction is in the blue. That's going to be the one then that changes the reaction pathway, actually lowers my activation energy. Notice here how I have some more intermediates that happen, okay, and then I have my product, but I have a lot less energy that has to go to get that one to actually go. All right. Same thing happens with a heterogeneous catalyst, except for something that is a heterogeneous catalyst. These exist in a different phase in the reacting molecule. Usually they are a solid. We tend to go with solids because they have very large surface areas, so there's lots of places the reaction can actually take place. A lot of times the catalyst will actually adsorb. Remember, adsorb means it sticks to it, the molecules, and will then bind to the catalyst, and that's kind of the faster reaction there.